Okay, so as we're looking at functions, we want to be able to identify places where the function is increasing or decreasing, where we have local maxes and mins. I'll tell you what local means. Concavity, we'll talk about that, and inflection points. So just being able to identify those 4 things in a function. This should be new. I'm going to give you informal definitions on these. There will be formal ones that you'll be given in calculus next year for all 4 of these. And you'll be given a tool called the derivative for finding all of these. So we're going to approach this from algebra and from technology standpoint. Okay. So increasing just means as you go from left to right, the function rises. Okay. So we'll just say increasing is rises from left to right. So we're increasing right here, and we're increasing right here, and we're increasing right here. And then decreasing falls from left to right. That's what it means to decrease. So we can see that happening here and here. Increasing, decreasing. And we want to be able to use functions to model things in real life, and we want to know if it's trending up, trending down, those types of things. So, local max and min. There's a difference between what's called an absolute max and an absolute min, or absolute max versus a local max. An absolute max would be the very highest point that the function reaches. That there actually isn't one in this one. It just keeps on going up. But we have a local max. A local max is just a high point on a small interval. Okay, we might call it a peak, but it's a high point on a small interval. And a min is a low point on a small interval. So I should back up a little bit. Increasing and decreasing is a specific interval. It's not a point. A max or a min is a specific point. And usually with local maxes and local mins, we just list the x-coordinate of the point. That's it. So we have maxes here. There's a local max here and here. So there's a max. There's a max. And then we have a local min here and here on our graph. Right, concavity, concave up versus concave down. Concave up just means that, think of it as it holds water, but concave up is the direction in which the graph is facing. So concave up, you could probably just take care of it with a picture. That's concave up. I'd say it holds water, like a cup, yeah. And concave down would mean it's going to spill the water out. It looks like that. And once again, concavity is described using interval notation. It's an interval. Sometimes it's hard to tell where it changes from concave down to concave up or vice versa. We might say, oh, this graph is concave down to about right here, maybe, and then it changes to concave up. Okay, so it's one of those things where it's hard to tell where it changes concavity. But with calculus, actually the second derivative, we can do it very explicitly. We can find the x-coordinate of the point where it changes concavity. So that's an advantage to calculus. So what we're going to do is we're just going to find what's called the point of inflection. The inflection point is the place where, and this is once again a coordinate like the max or min was, but place where graph changes concavity. And we're going to find that by just taking the average of max and min. Okay? So just add up the x-coordinates of the max and min and divide by 2. Okay, so find the average of the max and min. So I want to find this point of inflection right here where it changes from concave down to concave up. It's somewhere right in here. That's the point of inflection. It's going to be the average between the max and the min, and we'll estimate it that way. And then here, it's maybe right about here. There's another point of inflection here and here. Okay? So you can plot your graphing calculators. We're going to just graph the function and then go ahead and find the max and min, and then from the max and min you can get all those intervals. Alright, so we have this function. It's f of x equals negative 2x cubed plus 6x squared minus x plus 3. So I'm going to graph it. And then in that same window under second trace, you'll find the max and min function. So here we go. Go ahead and type that in. Type it in with you. Negative 2x cubed. Don't forget to use the negative sign, not the minus. 2x to the third plus 6x squared minus x and plus 3. And then we'll go ahead and graph it. And you might want to, if you need to, you can change your window to a standard graphing window by hitting zoom and Z standard number 6 if you need to. There's the graph of that function. And we're going to identify the intervals over which it's increasing, decreasing, maxes and mins, points of inflection. It's all going to be based off of what we get when we calculate the max and min. So if you go to second and then trace, you'll see on here we've talked about the value function and the zero function. Now we have minimum and maximum, you see here, 3 and 4. So let me go ahead and choose number 3, the minimum. I think the minimum comes up first. It's going to ask for a left bound. And then it's going to ask for a right bound, so I just need to make sure I get my cursor on each side of what I think is the local minimum. And it's going to ask for a guess, and then it will give me the minimum value of 0.087. I'm going to write down x equals 0.087 as a local min. The min, x equals 0.087. We'll take it to the nearest thousand. And then I'll find my max, going through the same process. So now that you know how to find zeros, this is pretty similar to that, right? So on my calculator, I go back to my calculator, go to second, calculate, number 4, and then go through the process of finding the max. So left bound, that's probably a good left bound there. Right bound, I want to make sure I'm on the other side of that, what looks to be the peak. Guess, just click one back. There it is, 1.913. So 1.913 is my max. All right, x equals 1.913. And once I have the max and the min, I can get all the other stuff on there, the other 3 things, just based on the max and min. Here's why. My intervals over which it's increasing or decreasing are decided by the max and min. Look at the picture here. There's my min. Up to my min, it is decreasing, right? Between my min and my max, it's increasing, and then after my max, it's decreasing again. So if I want to write down the decreasing intervals, I just have to use my min and my max to separate it out. So it's decreasing, let's write this down, DEC, decreasing, from negative infinity, and we're going to write it in interval notation, to 0.087, and then union, the other side of the max, it starts decreasing again, 1.913, comma, infinity. So that's the interval over which it's decreasing. And then it's increasing from in the in-between spot there, 0.087 to 1.913 is when it's increasing. All right. Yes? What's that? We're not going to use And then inflection points. We find inflection points by taking the average between the max and the min. So if we take 0.087 plus 1.913, add those up, divide by 2, we get 1. So we have an inflection point at x equals 1. So looking at the graph, x equals 1, you'll see is right halfway in between the max and min, so right about in there. So about x equals 1 is our point of inflection. All right, in the intervals where it's concave up and concave down, x equals 1 will split those two, there's that change on concavity up. So if you look at this, it looks like it's concave up to x equals 1, and then concave down. You can see the concave up here, up to there, and then concave down after that point of inflection. So write that down here. It's concave
Maggie
up
McClymont, please come to the counseling office. Maggie McClymont, please come to the counseling
from
office.
negative infinity to 1, and concave down from 1 to infinity. All right, one more topic here. It's called the average rate of change. Average rate of change is also known as the slope of the line. You may recall m equals y2 minus y1 over x2 minus x1. When you were finding the slope, you were finding the average rate of change. So if you're jumping out of an airplane, your instantaneous rate of change would be whatever speed you're going at that moment in time. Average rate of change would be the speed from, say, the time you jump out of the plane to the time you pull your chute. So the average rate of change is over a whole interval. So we're going to calculate average rate of change using our formula right here. All right, so we're given a function, 3x squared minus 2x plus 3. We're going to find our average rate of change from negative 2, we'll call that a, to 1, b, by plugging it into this formula here. So it says we're going to use g instead of f, but we've got g of 1 minus g of negative 2 divided by 1 minus negative 2. And so if we're not going to do the second example here, we'll get rid of that guy. So if I plug in 1 to the function, I have 3 times 1 squared minus 2 times 1 plus 3. That's the first term, that's g of 1, minus g of negative 2 will be 3 times negative 2 squared minus 2 times negative 2 plus 3. And that's all over 1 minus negative 2 will give me a positive 3. The top ends up being 3 minus 2 is 1 plus 3 is 4. So I have, this is 4. And 4, 12 plus 4 is 16 plus 3 is 19. So I have 4 minus 19, which is negative 15 over 3. And that is my average rate of change from negative 2 to 1 for that function. Just to give you a picture of what this might look like. It's the parabola here. It might be going from negative 2 to 1. So maybe we have a vertex somewhere over here, something like that. So here's negative 2. Here is, say, 1 down here. What I'm saying is this slope is negative 15/3. The graph shows the weekly sales for a company over a period of 10 weeks. Estimate the average rate of change of sales over the given intervals. So what we're going to do is, over any specific interval, say from week 1 to week 8, you see it here, week 1 to week 8, we're going to find the slope of that green line. So you would just calculate the slope by finding the two coordinates and then using your y2 minus y1 over x2 minus x1 equation. So go ahead and figure out the coordinates here. We're at 8, 1,000. And here we're at 1, 200. And so my average rate of change would be 1,000 minus 200 over 8 minus 1, which is 800 over 7, and then you can reduce it as you see fit. The second one, from week 4 to 7, looks like a negative average rate of change. We have a coordinate here of 4, there's 1,000, there's 1,400, and we've got 987, 800, and so we'd have 1,400 minus 800 over 7 minus 4. You guys can come on in. So that's 600 over 3, which reduces to 200 as my average rate of change. And the final one, from week 3 to 5. You'll see from week 3 to 5 I have no rise, and so my rate of change would be 0.